trying to organize something. So the only type venue that's available is available during this time slot. So what we're going to do, at least for next week, I'll try and do it so that everybody has access to Excel because it's easier to solve everything. We're going to switch around the TUT and the lectures. But because we're switching from a 2 hour and a 2.5 hour, the TUT test will still be on a Tuesday afternoon. So on Tuesday afternoon we'll start the test. So for everybody that's basically repeating and have clashes today, they won't miss the TUT test because it's still there. So we will start with the TUT test, and after that we'll do the lectures, right? And then, but I'll put everything on Sunlearn so that everybody can see, because I mean at the moment I see only half the class, so only half know about this at the moment. And then the TUT test, that will basically be on the work done up to the previous TUT again, like all the work done to there. So basically that gives you time basically to assess what you've done in the TUT of yesterday and manage to hopefully do well in the test. And the test will be, you won't be there in Excel for the test, so you'll be able to do just the calculator. Okay, so first things that I want to do is yesterday's TUT, and I'm going to just go through how to do it, basically how to use the solver, where to find the solver, and then also in terms of question 1 and 2. So our first question, and maybe just you can just keep up. This is basically this, my solve. It's a bit busy, but I try to put as much information on there, and I'll put this also on the as part of the on the TUT folder. So it's more important now to understand what's going on to try and copy it. I'll put this exactly on there. So first of all, this is my input parameters. So you'll see that on my question we have a wave depth, a wave period of 9 seconds, height of 6, and the traveling at a 60-degree angle. So that's my input parameters. First question, and you'll see this is all the input parameters in column H. You'll see just a reference to what's the equation in that cell, in the cell in column D. So for instance, this one is basically just, I've managed to mark that as T. So that's basically 9.8 T divided by 2 divided by pi. So, and that's basically this equation, right? Because we want to know what is CS0 at the deep water. This is my wave approaching in deep water, so I could highlight it with deep water as well. So that's my wave period at C0 GT over 2 pi. So I'll just calculate that. The same with L0. L0 is basically, it's all deep water, so that's my L0 equation. That's happening in there. I can calculate my K value for this specific deep water state. So I'm in the deep water state. I can calculate Q0, and then remember, important to note that if you look at that section, pick it up like that. The moment you work in Excel, Excel works in radians. So if you get something that's in a degree, you must first convert that to radians. Otherwise, it won't work. Okay, so let's just go up. Okay, so that means that we now basically so we can calculate our sin alpha. So we've got that. So the first, and that was all the parameters that was needed for A was, please get the deep water wavelength, and that's my L0 that I've calculated, and I can also calculate my K0. Then I think the question where everybody started to Okay, B was just what's the depth. So once again, notice on there that the moment I'm at D over L over 2, so L0 divided by 2, so I just take my L0 divided by 2, and that's the depth where I've got influence for my CD. So now, to solve question C, we now assume we've got contours parallel, so we can just do the standard solving. So the basic idea that we have here is that we want to calculate our H with our different coefficients K, R and Ks, and that should be the same as my breaking wave coefficient of HB over dB. So we're going to do calculations for both of these, and in the end we must have an equation that satisfies both of them. So they must be equal in the end. So for that, we can estimate and start with the L. So, and remember, when we're using the solver, you need to start off with values. So what I can do is I can say, okay, let's just start off with the 0 level of 63.2. And we start with our L, like the same as our L0. And now you'll see the moment you do the calculations, because K is now a function of that L that I've chosen at the beginning. This is just the equilibrium. I need this to be 0. I must solve this for 0, and that's just my equation where I get that value, which is a function of the length. And then also I can calculate my sin alpha over sin alpha 0, just a function between all of that. D15 over D17. And from there on, so now I can get alpha, so that's just the asin of the that's basically just sin alpha multiplied with my ratio, and I get my C value. C value once again, if I look at that, it's just C0 times my alpha, because if you look at this equation, all of the sin alpha over sin alpha 0, that's basically all of these different ratios. And once again, if you look at your Ks value, you get from this equation. So you can once again calculate all of that. You've set up everything. This is, this is not real, but this is the one that you start off. And then once you get that H, now you can calculate your H value. So that's this formula of yours. So H0 times KR times Ks. And that gives my H, and then I can use my equation and say, okay, that H multiply 1.28, that will give my breaking height. But now you'll see this depth, these two are different. They're not equal, and you want to get the neutral.
Ek wil gou weet, so with the subscripts over there, it's written as like D15, D7,
That's
D20.
Cell D, this is cell D15. This one.
Yeah, what does that mean?
This one is just the formula that's in the spreadsheet. So
it's the cell. Okay.
So for instance, maybe if it's not clear, maybe I'll show you just.
I thought it was.
This one.
I thought it was the depth.
Maybe a complication. So this one, it says D20 times D6, so it's D20 times D6.
Okay. Cool.
So that's only these equations is just to show you how this relates, because I mean this comes from this side.
Yeah.
So you see the arrow points to this one. This is my KR value, and this is the one that I'm substituting in there. So this is basically and this is the KS formula.
Okay.
So this is the formula, how you see, and this is basically just the formula as it appears in the spreadsheet.
Okay. Cool.
Happy?
Makes sense. Yeah.
Am I correct in saying that you could also read that KS from that shown table?
Yeah, it's on our table.
Yes, or shown table.
We can do the other type one as well. Okay, so now that we've managed this, the one thing you now want to do is want to make sure is that this value where there's a mistake in, so you can see you want to solve that's 0, and you also want to make sure that that's 0. So the one thing you can use for here now is you can use your solver. So
Cool. So you need to scan with the
okay, are you happy with that? Let's switch it to both sides. Okay, happy. So you should have, and if you don't have, you have to just make sure that you install the solver. The solver is there under your data analysis. There it should be, that's the what is data analysis format. So if I go to the solver. Now here, what I'm doing here is I can say I'm going to set an objective. So in this case, I'm taking D18, so this is that value. I want that value to be 0. By changing the cells here, so I'm changing the cells D14 and D15, so there's those two cells. And then also, I think the one we didn't do yesterday was that you can also add here some constraints. So I can add here another constraint and say, what do I want to do? So I just say, okay, something must be small or equal to or whatever. So in this case, I've added that this value also needs to be 0. So you can do it simultaneously. So the moment you do that, once you've done that, you can say solve. And then it gives you this results and say, okay, do you want to keep it? And then you just say yes. And now you'll see that's not actually your D with L values. I've solved this to be 0, and this is also 0.
Would we have to do this in the exam? Like a A2, or because it's going to be on the computer?
We're going to write on the computer, yes. We're going to write in the I'll organize a computer room for us.
Okay.
Because I mean it becomes difficult if you don't, and this is accurate in that case.
Yeah.
If we look at the same thing, but I'm not sure nobody do this way. But you have this tables, the showing tables available with all of these values, and you can actually read through it to make sure how do you do it. And I did manage to get some to finalize this. So basically in this tables you see you start off with this D over DL value. So you can do for different D over DL values, you can do that. And especially now if you do it in Excel, you basically have to put them in once and you get the answers. So basically if I have a D over DL, I know what's my L0, so I can calculate D. Then from this table, you see you can now also input the tan HD star, which is basically your approximation of that center term. So you see this center term is an approximation of that tan HKD at that specific unit. So still not 100% accurate, but a good estimation. So you can get that from the table. So that means, and if you look at your the table formula, it says L equals L0 times that tan HKD star, or See? And then you can calculate L. Now you can calculate L on L0, which is the same as C on C0, so you can calculate C. You can also, since if you have both of them, you need to get that center term, that's 2 star over sin HB, get that value. But in the case of this one, you'll realize that once you've done that and do the calculation, you can calculate the KS value. But this H over H0, since there's no other diffraction or something like that, we assume that that's basically our, if we look at back to our equations, we can basically say, okay, this is basically our KS value. So in the table, that is actually your KS value, so you can put your KS value in there. You can calculate your alpha. You can basically calculate from equation 8.10. You can calculate KS, calculate the real H over HB, and you calculate your A. And now you have a D star that you can calculate using basically this equation of 1.28 times the height. And you can now see what's the difference between the first one and the second one. Once you've done this for the first one, you can basically just do it for all of that. And now you're looking for the point where this difference goes from positive to negative or negative to positive, all depends on the calculation. And then you just can do a simple interpolation between this value to be 0 and that value for the L over D, and for the rest just do the interpolation for all of that versus the one you pick, and then you'll see now we get we were looking for our D, and our D is like 5.94, and in our original calculations 5.94. So we get close to the same answer if you do the sort of manual way. So if you're doing the manual way and you're going to do it, say for instance in the exam, you pick one, do it, and then just select one further on until you get and do this relation between all of that. But our way is basically, if you do it in Excel, do the real one and do all of that. Okay. Happy with that explanation, and hopefully I'll just put one of this screenshot of this also on the top folder so that you can have a look at it and see if you manage to get that. Because it's important to be able that you can actually do that. Okay. Quickly to while we at it. Our second question. Okay, who managed to get to the second question first? Just a answer. Oh, there's a lot of you managed to get to it. Okay. So, first of all, make a table of the way this wave is introduced from 100 meters to 1 meter depth. Assume no refraction and diffraction and or wave breaking. In the table is 100, 80, 60, 40, 10, 25, and 1. And then make a plot of these. Okay, so let's first do A before we make the plot. So basically what you can do is you have to, there's a few ways to do it. And that's, I'll quickly show you two different ways. The one way I've done it from a different angle, and the other way is the normal way of doing with the solver. But you can say, okay, I've got my different depths down here. I can start off with the K value. Or first of all, I've got my 11 seconds. I can calculate my L0 like normally, and I can calculate my L over 2D. Then I have a K. I can calculate if I pick a K at random. I can use that K value to calculate L, and then I can use the also that with the depth, the K, and also get the L, and then I can look and see, okay, what's the difference between my different calculations. So I've selected the K. I first do it in terms of my My first one just was in terms of doing, taking this formula, which is the part in the bottom to calculate my L, and the next one was just use the formula again with the KE. So the way you can do it now, you can say, okay, let's start with the K of, let's say 0.025, and then you can use the other part that's also available on the what if analysis to get the gold sheet. So I can say, okay, set that value, I want to set that value to 0 by changing that value. Once again, it's important to note that the moment you say you must change something, that must actually be a value in itself. You can't have a reference to something else, otherwise it will fail. And then when you do that, you'll see that it will change until you get to the right answer. So even if you start here, let's start at something like 0.05. That value should be 0 by changing that value. So you can now see how it will change. You can see the iteration process. The other way of doing that one, and this is maybe also in terms of, once again, because we're going to do a few of it. So to buy, for this one, that method, you basically have to do it step by step for every one of it. If you want to shortcut that one and say, okay, let's start, for instance, we start with all our L's at our L0. So we place that as values. Now I can once again use my solver. And you see, this one is now set up for, I want to, first you can only set one objective, but you can have all of these constraints. So that means I can set up and say that first value at the top, that difference, that must be 0. And I'm changing, you see, from N10 to N20, so I'm changing all of them. I'm going to change. But then I set the constraint, but all of these other ones need to be 0. So that's a way to bypass the solver, although, because they're not linked in terms of reference to each other, but you can basically solve everything simultaneously. So now you're supposed to get another, you see it takes a while, and now you say, okay, so there everything's solved. So that's a way to basically just put everything into one. And you don't need to do all of that. Okay, so now, I can do it on both sides, but maybe I'll do the one that I've done on this side. The next was basically just plot it. So basically the one thing we now need to make sure is that we now need to make sure if we do this calculation, we must always check in which of these three zones are we in deep water, zero water, or in shallow water. Which one of this is that one? So for instance now, you can say, okay, if I can calculate for all of them my L over D, so I can say, okay, this is my L over D, so it's 1.88, so that means, okay, I'm still in the deep water, so that means my final level there will just be my L0 level. The moment I get to the second one, now I've passed from the deep water to the green zone, so now I just take my calculated value. So that's now at 1.87, that 187.1 or 0.2, and so we go on until you get to a point, because I mean, if you look at your graph in the end, and this is the graph you want to plot, this is basically here somewhere between 1 and 20 and 25. I go over into my shallow water. In this case, the easiest, because this is it's somewhere in between, what I did in this case is say, okay, let's see, because if I do the shallow calculations for all of them, that's a straightforward calculation, you don't have to do any manipulation on that. The moment these two graphs cross, then I'm just taking the shallow water value. And that's in my final value, and that's the value that I'm going to plot. Okay, that will bring us to, and then the last one is just the deep water calculation. And in this case, they said ignore refraction, showing diffraction and energy losses. So in this case, this is just, remember now, what I know now is that basically if I go back to this one, these K values are all 1. So I know that value is still just 80. So 80 stays the same. So now I can calculate, I've got the 80, I can calculate my depth just by using my 80, and then I can just use the normal solving process to solve my length. So that one should be a bit more straightforward. So that's one iteration process. Okay, I hope this will help you in terms of what you were supposed to do yesterday, and hopefully what you can do in the exam. Okay. Okay, let's start and see where we can get to. Okay. Now we get to our lecture 5. Now we're getting our third zone processes. We've done everything until 8.3. Did most of the calculations, and you'll see what we need to do. So we'll now look at our general processes. So if you look at deep water breaking waves, we've done it where we break, where the wave breaking happens in shallow water. We've done that, but this breaking can even happen in the deep sea. The moment you get this HO over LO is at 1.7 or 1 divided by 7, that means breaking will happen. So that means we'll have some waves breaking in the open sea. And then with the shallow water, we have now done this we've assumed this 0.78 as our value, and this is known as gamma. In reality, this gamma is something between 0.4 and 1.2. So basically you can see from experimental output, this is what has all happened to the gamma value. We just use, for our basic calculations, we will stick to the 0.78. But if you're going to do something in practice and or some design work, you'll have to see exactly the influence of this gamma depending on the coast or whatever you need. Okay, and then, I mean, you know now this is 0.78. So the moment you see something like this, you know with this wave height, this is definitely not 0.78. Oh, so this is definitely distorted. AI generated photo stuff that you need to pick up these days is exactly how to spot it, and this is one of the things you must use. You must use your knowledge and see, okay, somebody created this, not the real photo. Okay, so now if we look at different breaker types, so you see this basically we look at 4, most of them is 2, so you basically look at your breaker type situation. So basically I can describe this epsilon beta can be described as tan beta divided by the square root of b divided by L0, where this tan beta just equal your slope. So if you look at this side, you'll see this is my slope. So the slope is just described as the vertical divided by the horizontal. So if this is 1, that is 2. Normally you will describe it in terms of 1 divided by a bigger number, especially when you look at our coastal type of stuff designs. So that means this is a half. So tan beta is a half. It's not done half by half, it is basically a half. So if you look at the different ones, so a spilling breaker, so there we've basically just got our spilling breaker, so it's just spilling at the top end. Once this epsilon beta becomes higher between 0.4 and 2, now we've got this plunging wave that is basically happening, so that is breaking a decent break, and then your surging breakers will basically just run up to the shore, especially in terms of some steep slopes and stuff. You see this, it's higher than 2, that's normally what's happening. You can see here a few pictures of a spilling breaking wave. So that's just your spilling breaking wave, your plunging breaking wave, and this is the most common breaking that you'll get. This surge breaking wave, and also this, there's also this collapsing breaking wave, which you very rarely see in practice. So you can see once again a few photos of our plunging wave. So we've got our plunging wave coming over there, and things like that. Nice surf. This is your typical wave for surfers. And then our spilling wave is just for our normal beachgoers, the easier wave that we can manage. Okay, yeah. So that's basically our different type of wave. And now we get to our surf zone and what's happening in our surf zone. So you see here at the top in our surf zone, when we get some our breaking point is that the moment. So we've got our standard depth value, and then now there's, due to this energy that's basically going to the displacement into our surf zone, there's some setup. So the water level is actually the little bit higher than the standing water level, the still water level. So there's a setup to that, and then there's also this run up in the end we'll get later too. And if it's really just coming forward perpendicular, that means that it will just go up and there. But the moment that there's some refraction, which normally happens with about 90% of the time, you get this force is now basically not perpendicular to my shoreline, but it's coming at an angle. So this got now a component which basically produces some long short currents. So if you look at this figure in your handbook, you see this long short current is basically in terms of this value, that line just looking to this side. So just look at it in terms of that to describe the velocity at any point in terms from my boating zone to my beach. So if I look at my wave setup and set down and set up, you'll see that's my that dotted line is now my still water level line, and then that blue solid line is my wave setup line, and then the light blue is basically just the normal wave breaking wind actions. So if you look at our setup, so you'll see in our handbook on page 259 to 261, we've got this basically action happening. So what's happening just after breaking, we first have some sit down. So there's a bit of a reduction in the level, and then it goes up, and we have on this side our wave setup. So for our reduction, you'll see we've got this equation. This is basically a function also of our breaking height and our K and our D values, and then the same applies to when we have our wave setup, and you'll see this is our depth where we're calculating it, and that is our breaking depth, and then basically remember this gamma function is that breaking depth height ratio that we're used to. And you'll see also the end of this formula, we're just ending up that last section is basically just that one. So it's basically our set down that we add onto that. So if you look at the equations in the handbook, you must remember this is a negative value. So that means the moment you add that value, that will reduce, because that top one is a negative value, and once again this tan beta that we have in this equation is just that slope. our setup line. Then something that's not in the handbook, but that is basically, and this is important for us in the South African case, is basically our wave run-up. So that means the moment the wave breaks, there's some extra height happening, which is the wave run-up. So in non-amateur, that's not big of a problem, but we've got some, we can have, in our case, this can actually in some cases be as high as our H0 height. So here's a typical example of now the wave run-up, and you can see the moment you get here to the end, this is normally our normal setup line on that side, but then at times as the waves break, you get some run-up, and when you design, you must take that also into consideration. The moment especially if you do some designs for critical heights or significant height levels. Okay, how do we determine this? There's basically two best practices that we can apply in South Africa for that. The first one is the Nielsen and Hanslow equation. So basically this is your 2% exceedance. And this is your equation of, once again, the WL, that's your still water level. So that's your tide, plus your surge, plus your sea level rise. That you really going to design for that, you'll use that. And that's 1.98 times 0.05 square root of beta. Once again, it's all depending where beta, I'll come back to beta, but this is now for cases where we had tan alpha less than 0.1. We tan alpha is your beat slope phase. Now your beta value, that is your H0 root mean square. So that's basically your, say, your variance of H0 divided by the square root of 2 times L0. When you go to the steeper levels, now that changed to 0.6 times, that 0.05 changed to 6 times the tan alpha. So now we take into consideration what's happening with the slope. The moment we get to greater slopes, we take into consideration the function of the slope. And like I said, you can also calculate your L0 and PS. There's some functions for that, and also your RMS is more or less approximation of your H0 is divided by the square root of 2. The next one is your matters. They've got it's almost the same as it also start the VL value. So basically that's the VL plus C plus H0 times 15 divided by XHS, and XH is the distance to your minus 15 meter controller. So that's also approximation, and your C value is something between 3 and 10, so somewhere you have to get that or get the estimation of that, and that basically will come to what's normally can be used. So this is just Dr. Prof. Karan's basically what he found with wave run-ups, the tested, and found that the best basically is these two that we're using, plus another one. We're not using that one at the moment, but in this course. And then also there's some adaptations that we can do for that, only in deep water heights. So once again, just make sure deep water heights. So our C coefficient we can set at 7.5. When we've got, once again, calculating our K value, which we've done. If our K value is bigger than 0.4, then we can use the C of 7.5. Otherwise, if it's less than 0.4, we can just use that 4. And then also the Nielsen-Hansen, you'll see this one was like 0.05. You can also just that change to 0.04. Okay. If we look at our longshore currents, once again, just this component that's working towards the southern side. And that means if we've got the angle at which this force comes into, so if you look back at our refraction part, you'll see this is my perpendicular line. So if the wave is coming at that angle, this is going to be my angle at which my long shore current is flowing, or created by my waves, getting to the shore. And this is your equation, and this is for your midpoint. So we can get a velocity for that, and that is 2.7 times UMD, and the UMD is once again that gamma of us, breaking height ratio, divided by 2 GT times the breaking depth to the power of 0.5. And then the last section that we need to look at also, and that's just waves, especially long waves, they can travel in groups. So you can get groups of larger waves and then a bit smaller traveling together, and this results in the secondary order waves, which can also have an impact on your runoff. And there's also some refraction and reflection of that wave from the sea, and that can also work together in causing the currents and that. Just take that also into consideration, that which means that your runoff can be a little bit higher due to this combination of all of that happening at that point. Okay, this was the first section of this. I think we can now take a break, and then we'll have to look at our waves and our short-term wave records and see how we're going to analyze that, especially now the heavy calculations come into play. Okay, let's meet about, say, 5 past. Start at 5 past.
You know what, if I was a ship captain in the Strait of Hormuz, you know what I would do? I'd send my ship full power through, right through the blockade. And then if they ask me, we will shoot you, and if they threaten me, I'll say, well, you can shoot me and send the whole planet into recession.